Hello, everybody again. This is Miss Peachy from WCA Physics A. We are looking today at Unit 5, Lesson 5, Conservation of Mechanical Energy. Our key words here are kinetic energy, mechanical energy, and potential energy. And I almost didn't make a video for this because this stuff we've talked about already, conservation of energy before. But there were a few things in this lesson that were either just new or they were a little complex in their explanation. So I just wanted to make sure we went through them. So let's dive right in, shall we? So the first couple of slides just talks about, energy and how energy is conserved. That they have mechanical energy can be changed from potential to kinetic energy. It talks about forms of energy as well. So we have this table here on slide 3. Looks at kinetic energy, which is 1/2 mv squared. Gravitational potential energy, which is mgh. Now it introduces a new type of potential energy, and that is elastic potential energy. And that one I demonstrated with the rubber band the other day to show you in one of my previous videos here. And we haven't talked yet about this, so I wanted to make sure I did take the opportunity to go through this formula with you, and that is this is equal to 1/2 k x squared. Okay, so potential energy elastic is 1/2 kx squared, where x is the amount you stretch your spring or rubber band. So if this is the resting position of my rubber band, I mark it from here to here, and then I stretch it, the difference between where this is and where this is now is x. So that's kind of how much it is being stretched, right? And K is something called the spring constant. And the spring constant is dependent upon the actual spring or elastic band that you have. So some are going to be super easy to stretch and some will just be a lot more difficult to stretch because of the material it's made out of. And that's what K is a representation of. Stretchy springs or stretchy elastic bands will have a different K value than those that are not as stretchy. They're harder to stretch. It takes more energy to stretch them. So you can use that as a form of potential energy too. So what's interesting is there's I don't know if it's something you guys will actually be doing, but if you think about like an oscillating weight on a spring, right? I don't really have anything I can hang from this, but let's just pretend I have a mass I can hang here. It's got a lot of, down here, it's going to have a lot of potential energy, and it's going to kind of go bouncing back and forth, right? So it'll kind of transfer the energy as it moves. A good way of looking at this is, let's see. So up here, I'm going to draw a picture. I think it's better than my rubber band. But if I have my little rubber band and you hang a mass from it, so let's say it's a little hanging, it's called a hanging mass. And here's the ground down here. The band here isn't really stretched out, and it's some distance above the ground. So from here to here is the height, right? So we can measure the gravitational potential energy of this mass as G, P, H, right? So I should say little g, but little g, pH. So gravitational acceleration times, oh my gosh, I'm just being dumb. mgh. So the mass of it times gravitational acceleration times the height. That's our potential or gravitational potential energy. I was mixing two things up in my brain. Okay. So up here, it's got a high amount of gravitational potential energy. When the rubber band is stretched, down here, the height is much lower. So it doesn't have very much gravitational potential energy, but it has a lot of elastic potential energy. So down here, you have a high amount of EPH is high, or EPE is high, right? So it's kind of going back and forth between high amount of gravitational potential energy, but low amount of elastic potential energy, high amount of elastic potential energy, but lower amount of gravitational potential energy, right? But they're always going to be equal and opposite of each other. So energy is conserved because it's changing back and forth between potential gravitational energy and potential elastic energy. It's going back and forth between them. So that's another way of looking at conservation of energy. Then we have some more questions that are being asked, and then it gets to a different example here with a pendulum. And I wanted to kind of go through the pendulum with you. So think about a pendulum as like you have a string and you got something hanging from the string and it's swinging back and forth. It's oscillating back and forth. So I can hang a mast from this. I could hang my pen, for example, as my pendulum bob, like that. When it's straight down versus up here, oscillates back and forth, right? So straight down, that's its resting position. It has zero amount of gravitational potential energy. When I hold it up, it's going to have gravitational potential energy because it's above where the resting position is. And then I let it go, and that's converting from gravitational potential energy to kinetic because it's moving, right? So high amounts of gravitational potential energy, low amounts of kinetic energy. Gravitational potential energy is decreasing, kinetic energy is increasing, right? Most amount of kinetic energy. Now it's increasing its potential energy, decreasing the kinetic energy, highest amount of potential energy, going back, increasing kinetic, decreasing potential, kind of keeps doing that back and forth, right? So what's saying here is kind of that's, again, another example of conservation. Now it's telling you that you can actually measure this using a little bit of geometry. So essentially, your string is not going to change in length. So when it's here versus when it's here, the string length does not change. What changes is the height above the resting position. So if this is your resting position here, this height here determines how much potential energy your string or your bob, it's called a pendulum bob or whatever, the mass is going to have. So the higher you would hold that up, the more potential energy it has, right? So you can actually determine that by using a little bit of geometry. If I were to draw a, let's see here. Oh yeah, that's how it is. A straight line here. That was not a very good picture because I can't do it. But I want to form a right angle here. In order to do that, I'm cutting off a little chunk of my string. But that's not really, we're not really cutting it off. What we're saying is that this here is equal to the height here. They're the same. The height above is the same. If I were to cut this off, this height, I don't know how to go back. It's actually this height right here. They're equal, right? So that's equal. So what I'm saying is if I can determine the length of the hypotenuse, what you can do is you can take the length of the hypotenuse and subtract the length of this leg, and that gives you the height. So we're trying to figure out this length here. If I take this length and subtract this length, it's going to give me that chunk, which is the height of my mass. So that's what it's showing you how to do there. Remember, we kind of did some of this previous with our kinematics and our vector problems and stuff, but if the length is the hypotenuse, leg squared plus leg squared equals hypotenuse squared, right? This is also a function, a sine function, cosine, tangent function, SOHCAHTOA. So if we know this angle, and we're going to call it theta, um, this leg length is opposite, or is adjacent to, it's adjacent to the angle. So adjacent, hypotenuse, adjacent over hypotenuse is cosine. So that's how we determine that this is L cosine theta, because this angle is adjacent to this leg. So that's what it's doing. So you can actually use a little bit of trigonometry to figure out the actual height of it. And once you know the height of it, you know you can calculate potential energy, because gravitational potential energy is mgh. So we know the mass, and we always know that little g is 9.8, and we know the height. We can now determine how much potential energy this little mass had in this position. So it's just kind of walking you through that a little bit here. And I think that's pretty much the gist of this lesson. I mean, it gives you some sample problems to work through as well, and give you some more scenarios with that. That's pretty much all of the content that goes through in this lesson. Again, just main ideas being that energy is always conserved. It's in a elastic band. It's changing from elastic potential to gravitational potential, but the total amount of energy remains the same. In an oscillating pendulum, it goes from high amounts of potential to high kinetic, to high potential, to high kinetic, to high potential, to high kinetic, right? And you can use a little bit of trig to figure out how much actual energy there is. If you have questions on that, let me know, everybody. Otherwise, I'll see you in the next lesson.